Let's consider the general form of the solution of a linear system in more detail. The general solution is equal to a particular solution plus a homogeneous solution. That's the slogan. Let's see what this means. Considering the four-variable two-equation system seen in a previous video, we found there that it has solutions of the following form. A constant vector, 4, minus 1, 0, 0, not multiplied by any variable, plus two vectors, each multiplied by a free variable, z and then w. Choosing z equals w equals 0 shows that the first vector is that particular solution with all free variables set to 0. We will always call that solution of any linear system where you set all the free variables to 0 the particular solution of that linear system. It turns out that every solution of a linear system follows the same pattern, a particular solution plus what's called the homogeneous solution. Why is it called the homogeneous solution? Let's see. A linear equation is homogeneous if it has a constant of 0, so it can be written as linear combination equals 0. A linear system is homogeneous if all the equations in the system are homogeneous. With every non-homogeneous system, there's an associated homogeneous system obtained by setting all the constants on the right-hand side of each equation equal to 0. For example, if we consider the original non-homogeneous system with constants of 2 or 9, we can just set those to 0 to obtain the associated homogeneous solution, as shown here. If we consider since the left-hand sides are identical in both systems, we can use the same row operations to convert each to echelon form. Shown here is the conversion for the homogeneous system. If we write the equations out, we find that the solution is as follows. The particular solution is the 0 vector, and the second piece, the two vectors, are identical to the vectors in the non-homogeneous system. And if you compare the two, you can see that this is the case. That's why we call the two vectors in the non-homogeneous system the homogeneous solution, because the homogeneous solution, the two vectors in the full solution solve completely the associated homogeneous solution. Okay. This is always true. The free variable part of the non-homogeneous system equals the full solution of the associated homogeneous system. This claim requires proof. The proof is approached via the proofs of these two supporting claims. A lemma is a supporting proposition. Lemma 1, concerning the form of solutions of any homogeneous system. For any homogeneous system, linear system, which has m greater than or equal to 0 free variables, in an echelon form version of the system, there exist m vectors, beta 1, beta 2, up to beta m, one for each free variable, such that the solution set of the system looks like the following set. A 0 vector plus 1 vector times a free variable for each free variable. If m equals 0, the solution set only contains the appropriate 0 vector. Lemma 2, concerning the division into particular and homogeneous parts. For any linear system, the solution set is either the empty set, or given that there's at least one solution, for any particular solution P, the solution set equals P plus H, where H satisfies the associated homogeneous system. In words, the solution set of any linear system is either empty or equals the set of vectors included in G. The general pattern. Any linear system solution set is empty or has this form. A particular solution plus a linear combination of vectors, one for each free variable, composed of a free variable times that vector. A corollary, or result that follows on this, is that the solution set of a linear system is either empty, has one element, or has infinitely many elements. Here's a summary of the situation so far. In the table shown, the columns represent the number of solutions of the homogeneous solution. The rows concern the solution of the general system. Given a linear system, we can tell which column applies to our system by whether it has any free variables. If it has at least one free variable, we have infinitely many solutions. If we're dealing just with a homogeneous system, we always have a solution. So the homogeneous systems are always in the first row. If we don't have any free variables, we have a unique solution for the homogeneous system. If it has free variables, the homogeneous system has an infinite number of solutions, but if it does not, then it has only a single solution, the zero solution. However, we do not yet have a similar general criteria which can be used to determine which row applies to our system. So we don't know. We know by the associated homogeneous piece whether it's either unique or infinite if there is a solution, but there might be no solutions, and we don't have a way of determining which row we're in. This is a matter for further investigation.